of noise can be from man-made and also comes within our electronic circuit itself. So all this noise will be summed to our system. So what are the effects of noise? Okay, the effects of noise. Anybody? I'm admitting some more friends, and that's why I cannot continue. So if you can just give some idea, the effects of noise. Jason? Okay, so basically it will affect the quality of our received signal. Yeah, distort the information carried by the signal. So the receiver is supposed to understand the original signal. Will have trouble to understand the original signals, and this affects the efficiency of communication system. Okay, so noise basically it is random in nature, yeah, and normally it's represented using statistical properties like our spectral density. Okay, so yeah, it affects the quality of our output. Yeah, can't see anything. Are you sure? Maybe line over there. It's not very good. Okay, I just want to illustrate the effects of noise here. So we have our, at the Tx is transmitter, Rx is our receiver. So we have spectrum of our signal. Yeah, we have peak at the center, and then so along the way we have our noise. Yeah, so this like these edges from our noise. So at the received signal, these two signals, the information signal and also the noise signals, they will be added. So this is basically the one that we received at our receiver. Okay, Abdul Ghani said cannot see anything. What about the rest? Can you see?
Yes, Doctor, we can see.
Okay, good. So I'll continue. Okay, so this is the one that we received. It's original signal mixed with our noise signal. Okay, so normally at our receiver, we have filter, bandpass filter. And this bandpass filter, one of the function is to eliminate, to reduce the impacts of noise. Okay, so the blue, this blue box is the bandwidth of our bandpass filter. So signals that fall within this bandpass filter's bandwidth will be processed for, sent for further processes. And so noise that exists within this same frequency as our bandpass filter cannot be removed by the BPF, is obvious. So it will be sent together with the signal for further processes. So, but today in advanced system, we have more intelligence processing at the back of our receiver to reduce the impacts of noise. Okay. Okay. I hope you can join our class at the specific time, because otherwise it kind of because I have to stop and then let you in. So next time, make sure that you come punctual, you join punctual. Okay, I've done this part. So you can compare the clean and the noisy signals, between them. Okay, so next, the sources of noise. Noise can be from internal, from the device or the electronic circuit itself, or from external, external of our circuit. So internal can, the two noise types, the main noise types within internal known as thermal noise or Johnson noise, and another one is short noise. Okay, so for thermal noise or Johnson noise is due to random movement of electrons within the conductor due to thermal agitation. So here the keyword is the thermal agitation. So even we do not apply any voltage yet or current yet to our circuit, this noise can still occurs because of the increased temperature. So we have heat in our system, so this leads to noise, basically. So short noise, we apply current or voltage, but because of the random arrivals of carriers, we know that the current, because of when we combine electron and holes, and at the output element of our electronic device, these carriers comes randomly. So this cause fluctuation to the generated current. So that's why it's called short noise. Okay. Next is external noise. So this can be from environment, whether it's man-made or natural. Man-made is like ignition. Natural can be lightning. Solar noise from the sun. Crosstalks can be from other systems that near to your system. Oh, you have capstone before this. All right. I have also capstone after this too. Okay. All right. So basically, noise is the main enemy in communication system. We have our communication system so that we can deliver information to the receiver, but somehow disrupts the process. So it affects the signal that we intended to send in the first place. Okay. All right. So the type of noise that we want to focus for this course is thermal noise. So this is our main focus for this course. Just concentrate on thermal noise. So like I said in our previous slide, so it's generated by thermal agitation of the charge carriers inside the electrical conductor in equilibrium, and it happens regardless of any applied voltage. So basically, the temperature increases. This leads to increasing movements of the electrons, which forms kinetic energy inside the conductor due to the increased temperature. And this kinetic energy will lead, the increase the movements of our electrons lead to current. So this noise current eventually lead to noise voltage. Okay. So because it's influenced by temperature, it's called thermal noise. So there are also other names for thermal noise like Johnson or Nyquist noise. So this is after the scientists who discovered them. And white noise. Why is it called white noise? Because it can happen at very wide, WIDE, wide frequency, and wide bandwidth. So that is why it's called white. Because when you say about white, and you refer to this on spectrum, and it means white light. It has very large bandwidth. Okay, it's like your rainbow. Rainbow. Before, okay, we have rainbow due to what? Rain droplets, and also sunshine. So basically, the droplet acts like a prism. And then the sunlight, the white sunlight, will be refracted, and you can see the 7 colors. So these 7 colors are these colors are all, they belong to different frequencies, and all these frequencies actually belong to this original white white light. So that's why it's called white noise. It refers to signal or spectrum with very large bandwidth. So thermal noise is supposed to have it can present at a very wide frequency range. Okay. So let's continue. So this is the nature or the origin of our thermal noise. Okay. So these two scientists, Johnson and Nyquist, they discovered, and able to explain. One of them discovered, another able to explain the existence of thermal noise, and they later proved that this noise power from thermal noise is proportional to the temperature and also bandwidth. Okay, proportional to temperature and bandwidth. So the equation for thermal noise is equal to KTB, where K is the Boltzmann's constant, and 1.38 times 10 to the power of minus 23 joule per Kelvin, temperature in Kelvin, and bandwidth in Hertz. Okay, so this is the equation for thermal noise. Okay, so this noise can be modeled using Thevenin or Norton equivalent circuit. Okay, so these circuits you have already learned in your circuit theory, right? Okay, so we can model it by having a voltage source that represents the source of our noise voltage, and then connected in series with ideal noise-free resistor. Okay, so this is Rn, originally our noise source, and then we represent it by using Vn, noise voltage source connected to the noise-free resistor. Okay, so this is from our thermal noise power, and then to understand what it is impact on our circuit, we will connect it to a load. Yeah, so using maximum power transfer concept or impedance matching, where it can be proven mathematically. So Rn is equal to RL. When Rn is equal to RL, all the power from Pn will be transferred to the load. Okay. So this is our thermal noise source. This and the other part here is our load. So when we connect, the maximum power transfer happens when Rn equal to RL. So we know our noise power. So now we want to derive the noise voltage Vn. Okay, first we find our VL in function of Vn. Okay, so what is our VL? So since they are connected parallel, so VL is RL over Rn plus RL divided by V times Vn. So Vn, so since RL is equal to Rn, we can simplify VL equal to Vn over 2. And next we find PL. Since we know VL, we can find PL, which is V squared over R. And then we substitute our VL, which is Vn over 2. Then we get Vn squared over 4R. Okay, so we have PL now. Next, we know that Pn is equal to PL. Since we assume Rn equal to RL, maximum power transfer, so all the power from our noise transferred to load. So Pn equal to PL equal to KTB. And then Pn we know is equal to here, Vn squared over 4R. So Vn squared over 4R equal to KTB. And then our Vn finally is equal to square root of 4 KTBR. So from Pn, we're able now to derive our Vn. attendance taken by reflection. Yes. So reflection due tonight, midnight. Okay, so any questions so far on this part? I got the reflections are quite useful because I can get some feedbacks. Yeah, so many feedbacks say that I should go slow, right? Especially when explaining all this mathematics equations part. So any problems so far? Okay, continue. Any response? Yes. Okay, continue. Good. All right. Let's do one exercise. Okay. So we have one operational amplifier. The frequency range is between 18 to 20 megahertz, and its input resistance is 10 kilo ohm. Calculate noise voltage at the input if the amplifier operates at ambient temperature of 27 Celsius degree. So who wants to try? Anybody?
Doctor, we can't see the screen.
Yeah, sorry? You cannot see the screen?
Okay, now can.
Okay. So here, you can take all the, extract all the necessary information from the solution. Okay. So I'll just give solutions first to some of these exercises, and then I will let you do your homework later. Okay. So bandwidth, like I said in our first class, basically is the frequency range, and here it refers to our device, bandwidth of our device of interest, which is op-amp here. So it's 2 megahertz. So our resistance are 10 kilo ohm. Okay, so we just use the formula, our previous slide, which is square root of 4 kTBR. Don't forget, temperature, you have to convert from Celsius to Kelvin, so plus 273. Okay, and then you need to remember this Boltzmann constant, 1.38 times 10 to the power of minus 23. So just solve, yeah. And then it's 18 microvolt. Okay, let's look at other parameters that help us to understand noise better. Okay.
Doctor,
So in our introduction, yeah.
May I ask why just now it's 20? The frequency is 20 megahertz. I mean, like, why don't? Yeah. How do we know the frequency?
Okay, here it says 18 megahertz. So we need to calculate bandwidth B. Yeah, so it's the minimum frequency is 18 megahertz, the maximum 20 megahertz. So bandwidth we just minus 20 and 18. So we got the bandwidth frequency range 2 megahertz.
Oh, okay. All right. Thank you.
Problem. Okay. So SNR, signal to noise ratio. It's for analog system. For for digital, we have special parameter known as the bit error rate or probability of error. Okay, so this SNR, actually we can calculate SNR at many points in our communication line. So if it's at the input, it's SNRI input. If it's at the very end, at the output of our system, it's SNR out. So SNR out is always less than SNR in. Logically, it's like that because of the existence of noise. Since noise can occur at many parts in our communication system. So it's added to our SNR. Okay, so we have many processes, and during this process we can add noise. All right, so let's take an illustration using wireless system. Okay, if we're talking about wireless system at the receiver, at the antenna we received our signal, so we can put here as our SNR input, and then we have filtered to get rid of some of the noise that is outside of our band, and then we can amplify our signal, and then we could have cables that bring us to another component. Yeah, so like this dam is demodulator, so we can have noises added to inside all these components or devices. So since the output here is our SNR out. So since SNR out is less than SNR in, so since noise, since noise is added to our system, then that's why SNR out is much less than SNR in. So this is an example from wireless. For cables and wired, you can have your transmitter connected using cables to your receiver, and in between the cables you can have gains. So in this case, SNR in can be assumed at the transmitter, at the receiver is our SNR out. Okay, so whether it's in or SNR out depends on the system that you want to study. Okay, so all right, can we continue? Any question? Okay, no question, I continue. Okay, so that is some description on SNR. So apart from SNR, bit error rate, I'll talk later in digital chapter. Okay. Apart from SNR, noise voltage, noise power, okay, other parameter related to noise, noise factor, and noise temperature. Okay, so signal to noise ratio is basically our signal power divided by our noise. Of course, which one is better, larger SNR or smaller SNR? What do you think? Which one is better, a large SNR or a small SNR? Hello? Yeah? Large. Okay, good. Large SNR. Large SNR because it means the gap between signal and noise is higher. So it's easier to differentiate our noise. So noise factor is when we divide SNR in by SNR out. SNR input divided by SNR out. So it's also known as ratio of ratios because it's the ratio of SNR in and SNR out that are also ratios. Okay, so I just want to remind you, so many students got this careless mistake. Sometimes they, instead of SNR in divided by SNR out, they do as the inverse, SNR out divided by SNR in. So since normally F is higher, larger than 1, so your SNR in, which is bigger, should be above lah. And then this is noise factor, SNR in divided by SNR out. Noise figure is just the dB. You convert from noise factor to dB, so this is your noise figure. Okay. So when you convert to dB, normally we don't change name, but for noise factor, we change the name. Instead of factor, it becomes figure. Okay, so noise figure and F is just 10 log F. Okay. Any question? Okay, so by the way, your introduction and noise, this will be assessed in your first test together with AM and FM. It won't be assessed in your final exam. Okay, let's look at the other parameter, noise temperature. Okay, so we know that noise can exist in many components, but for the purpose of our analysis, we use amplifier for our model, amplifier with noise. Okay, so here we have our amplifier, and we have input noise and output noise. And we know that amplifier has also its own noise, which is NA. Okay, so the output to our the output noise from our amplifier is in function of Ni and Na. Ni is the input noise from the previous stage, and Ne is the input noise from the amplifier itself. So in this case, we have to add Ni and Na, and both of them will be amplified by the same factor G, and G is the gain of this amplifier. So our NR is then G and I plus G and E, where this NE is the input noise of the amplifier. Okay. And the noise power, we assume, since we assume thermal noise, then we follow thermal noise equation, which is KTB. So if it's from our input, noise from our input, it's KTIB. If it's from our amplifier, then KTEB, something like that. Okay. So okay, or am I going very fast? You can follow. Okay, we have question here. You mentioned about impedance matching. What is the significance of it in relation to the noise and the load? Okay, impedance matching is when R from our noise source is equal to R at the load. In this condition, when they match, noise power is equal to noise at the power at the load. If Rn not equal to RL, if they don't match, then you do not get this condition of Pn equal to PL. Yeah. Why do they do it? Because we want to derive. Okay, we have noise source. We want to derive noise voltage. So that's why we connect it to the load. Basically, it's a modeling. It's okay, Jason said, why do they do it? Is it a way to find the noise? It's the way to represent, to find the noise voltage. Okay, we have noise power, we know noise power, but to find noise voltage, we need to model using circuit, circuit level. So, and that's why they come up with this model. Okay, so it's a way for analysis lah. For analysis. Like this one, we want to find the noise temperature, TE. Okay, so we want to find the TE, right? Okay. So this is our amplifier, and that we want to use as our model. So input, we have two types of input, and this original signal SI and also the input noise, NI plus NAI. Okay, so this NAI okay, sorry for the mix up. And so this is also similar to NE lah, which is the amplifier input noise. So we have here our noise factor SNR in divided by SNR out. So SNR in is SI over NI. SNR out is, okay, our S out is equal to GSI. Yeah? And our noise out is equal to G times NI plus NAI. Okay. So in this case, we can cancel out the GSI. So we're left with NI and NAI. Okay, so it becomes 1 plus NAI divided by NI. So F then is equal to 1 plus NAI divided by NI. And then since N is equal to KTB, we can further simplify, cancel out the K and B, becomes TE over TI. Okay, so TE is then our noise temperature, which is equal to, if you let it become subject, then become F minus 1 divided by times TI. Okay, so this is the derivation for noise temperature. Okay. All right, so now we have derived, we know the noise power, derived noise voltage, look at our noise factor, SNR, noise figure, now it's noise temperature. Okay, so let's do one exercise. Okay, can you see the exercise? So we have our noise generated in amplifier. So in this case, the bandwidth is given 5 megahertz. Yeah, it's represented by amplifier input noise power 0.082 picowatt. Calculate noise factor and noise figure. If the amplifier was fed with the source input signal, match the temperature of 300K and then just repeat with 100K. Okay. Okay, so what do we have here? We have our bandwidth, our NAI, we know, and we also know our input temperature 300 Kelvin. Okay, so let me give the solution for the top, for the A part. All right, so you know our F is 1 plus NAI divided by NI. NAI is already given, just need to calculate NI. So you know our TI 300 Kelvin, we know our bandwidth 5 megahertz, and then we Boltzmann constant, need to memorize. Okay, so it's around 2 times 10 to the power of minus 14. So when you solve this, you get nearly 5, 4.96, the noise factor. And noise figure is just 10 log of our F, is 6.95 dB. Okay. Any question on this? Any question? So NE is equal to NAI, yeah. It's actually in this and in the slides, they refer to input noise, amplifier input noise. Yeah, you can use both symbols, an E or an I. Okay, any other question? If no question, I'll ask you question. Okay. Okay. All right. Why don't you try for B and see what is your answer? You can just share your solution on the Telegram, snapshot, share in Telegram. So I'll give you like 5 minutes to solve. Okay, so after 5 minutes, I will just ask anybody randomly. So please prepare. I think 5 minutes is too long. You don't need that 5 minutes. 1 minute is enough, right? Just change the temperature. Okay, first I want to ask for volunteer. Anybody? Okay. So what's your F now? Your new F? Okay. So maybe you want to share, Esther? Esther? Can you share your answer with the class in the Telegram group? Where's Esther? If Moni, okay. Okay, meanwhile, if we can have someone else, then we can compare the solution. Okay, someone has left. Okay, 11.1 dB. Can you just share your solution? Okay. So 11.1 dB. What about the rest? You got 11.1, yeah? So it's very straightforward. So you can share your solution later. I just calculated. Okay. So yeah, it's very straightforward. I just change instead of 300 to 100. So you got 11.1 dB. Okay. So yes, correct. I'm gonna share the solution here. Okay. So I'm not sure if you have time for another exercise. So yeah, you can try this at home. Then we can discuss your solution in our next class. Okay. So in our next class, we'll continue with noise. Yeah, but this one is we consider many stages, not only one, yeah, but few stages, at least three lah. Because logically, as in our communication system, it's a cascade of components or devices. Yeah, so we need to know what is the effective SNR, for example, what is the effective F, considering all the stages. Okay. So, any other question or anything that you're not clear for, of today's lecture you want to ask? Okay. So, no question. Okay. Just one last question. If our F is equal to 1, what does this mean? Okay, so it's just kind of open-ended. Okay. No calculation, just give your thought. Okay, let's choose someone. All right. Oscar?
Yes.
Okay, F equal to 1, what does this indicate? Any idea?
No.
Okay, so Esther said no noise. All right. Okay, so why don't you just signal and noise is the same level. So that is SNR, right? SNR. If SNR is equal to 1, then S and N same level. Is F equal to 1? Ideal situation. Okay. Yeah. So it's when noise, the system does not add noise to this. So there's no added noise in the system. Okay, so that's why SNR in is equal to SNR out. Not only noise, but your power also is the same. Does not experience loss, or the losses are compensated the same level as input signal. So SI basically is the same as S out. So this is when we have 1 lah. F equal to 1. Okay, so can you share your solution, please? Anybody who calculated 11 dB? Okay, so that's the end to our today's session. So I'll just stop recording. So